Swayam Prabha. Digital India. Educated India.
To handle this, we need to see that how we can simulate this wave flow, and then how we can take protective measure, preventive measures. So, for all those, understanding wave is very important, and as such we started with what are the different types of wave, how we can classify waves, and then as I am just saying that how the wave propagate, that is very important for our various requirement, practical requirement. That is why the speed of wave propagation is also necessary, and there comes the term that we call as celerity. Well, what we mean by celerity is that it is the speed of wave with respect to the fluid media. Well, if we just simply say that celerity is the speed of the wave, then it is not complete, because we need to say that it is in reference to the fluid media. If the fluid media is at rest, then of course the speed of the wave, absolute speed of the wave and celerity will be same. But if the fluid is also moving, and then over that fluid the wave is moving, then celerity is the speed of the wave with respect to the fluid media. And for analyzing these wave, say what is the celerity, to have an expression for the celerity, when we try to analyze it at unsteady flow, we face some complexities, and this unsteady flow, therefore we try to convert to an equivalent steady flow, so that it become convenient for our analysis. And in last class we did so how we can we could see how we can convert this to a equivalent unsteady flow, and we are starting from equivalent steady flow, and we are starting from that in this class. Well, say this is a wave forming here, a solitary wave, single wave, and the bed is there, and by say and let us first consider that this is a still water, maybe in a tank, and by moving a paddle we have created a wave, a single wave is moving like that, and it is moving with a speed c. Well, and this is a unsteady flow. This is a unsteady flow. Now, to convert this to a steady flow situation, as I did explain in the last class, that like a walker, as the belt is moving upstream, or say when we walk, the belt move in the opposite direction in a walker, and that is why although our that we are walking on a walker, but we are not moving forward, and then someone can observe us that how we are behaving when we are walking, but we are in a steady position, we are in a static position. So, that advantage we can have here, like the belt move in the opposite direction in a walker, we can put a opposite direction, the velocity c, which is the actual velocity of the wave. Then what will happen, that this is also moving in a velocity c, wave is also moving in a velocity c in this downstream direction, and as now this fluid media is moving in the opposite direction with velocity c, and wave which was moving in the downstream direction with a velocity c. So, relative velocity of this will become 0, and then it will be remaining in this position, and now we can observe it carefully. Well, now let us see how we can analyze it. Say this depth b at this section, suppose at this section depth b y, and so amplitude of the wave is say a. This is the amplitude of the wave. And so, what will be the depth here? Depth in the wave portion where we have the wave, this will be say y plus a. Well, and when we talk about velocity, then c is the velocity at this section, say section 1. And if I talk about the section 2, then what will be the velocity? Say velocity is v, because this velocity will not be equal to the velocity c, because depth here is changing. So, let us write this velocity as v. Well, now we can write a continuity equation, and from that continuity equation we can find that how we can express this V and C, how we can relate this V and C. Well, how we can write the continuity equation? Say if we consider this channel to be say rectangular, and suppose we are considering unit width of the channel. So this is okay, let me just write here, this is a equivalent steady state. And now let us see the continuity equation, how we can write say continuity equation. Between section say 1 and 2, between section 1 and 2, how we can write, and that we are writing considering unit width of the section, unit width of the section. Well, we are considering unit width of the section. Then what will be the discharge? In continuity equation state that here the discharge and here discharge will be equal. Discharge at section 1 and section 2 will be equal. Fine. Now discharge is equal to the velocity at this point 1, section 1, and the area. Area is equal to y into its width. In fact, if we consider width, then width will be coming, but we are considering width to be equal to 1. So it will be c into y. So what we can write, that c into y is equal to, here we are talking the velocity as v, so v, and depth here is equal to y plus a, y plus a. And from this what we can write, that v is equal to c y divided by y plus a. Okay. Let us keep this expression here, and now we can write another expression. This is from continuity equation we are getting this relation, that is b we can express in this form. Well, but we can have another expression from the consideration of say energy equation. Now what will be the energy at this point? It will be y1 plus, that means at section 1 it will be y1 plus, sorry, y, we are writing y plus c square by twice z. And here, because velocity is c here, and here it will be y plus a plus v square by twice c. And let us write that expression. Well, and we can write that energy equation energy equation between section 1 and 2. Of course, when we are writing energy equation between section 1 and 2, and we are saying that energy at this section at that section are equal, what we mean that there is no energy loss in between. That assumption is inherent there. Well, now let us write that expression, say y plus c square by twice g, that means v square by twice z, v means velocity square by twice z. This is equal to depth in the section 2 is y plus a plus say v square by twice c. Okay, let me write one step, v square by twice c. Now what this v is? We know that v is equal to c then y by y plus a. So we can just replace it in this form, that is y plus c square by twice z is equal to y plus a plus, you can write that c square this in place of c square by y plus a whole square. So v square, we can write that v square by twice z will be, and v we can write c square into y square by y plus a whole square. Okay. Well, this is the expression, and from this let us try to write, because our interest is to get an expression for c, and here what is not known and what we want to try is the c, and what is our unknown thing is y, a here, the amplitude. And at the same time this expression we are writing for a wave where the amplitude is very small, I mean small amplitude wave. As we just if we recall our last class, then we were talking about one expression that C is equal to root over gy. For rectangular channel we obtained that, and that was for small amplitude wave. So, here also we are considering that this drift is considerably large than the amplitude A. Well, let us just separate this term and see how we can write it. This y and y will of course get cancelled, and let me write first A in terms. A is equal to, then c square by twice z, c square by twice z is here. So, we can bring c square by twice z, and then we can write 1 minus say y by y plus a whole square. Well, and this can be written as, say, let us break up y c square by twice z. Our intention is to see that if, because in the expression of c, in fact we do not have the a term root over say gy, that was that's what we got in the last class. So, let us see, by we are starting from the first principle and we are trying that yes, if we can get this expression, and here we do not have a term. So, let us see how we can do that, and this we can write say y plus a whole square, and then this will be, say, we can break up y square plus twice a plus twice a y square plus twice a y plus a square, then minus y square. Well, here we are in a position to simplify now. Well, so what we can do, that from here let us write one expression for c. So, c is equal to, we can write that c is equal to twice g a will be coming, c square, let me write c square is equal to twice g a, and then this will be just, we can write in the reverse direction, reciprocal of this one. This will be say y square plus twice a y plus a square, this is there, and here what we will be having, this and this is getting cancelled already, and here we have twice a y plus a square. So, that twice a y plus a square we can write here as a keeping common, and we are writing twice y plus a. Well, now this a and this a we can cancel at this point, and let us see how we can write this expression. Well, so we can write c square is equal to now root over twice g, and entire things we can put under root sign, root over twice z, and then here it will become say y square plus twice a then twice y plus a. Let me start from this expression again, y square plus twice a y plus a square divided by a twice a plus a. This a and a is getting cancelled. So, what we are writing, that twice z, and in this part we are writing that expression, well, plus a square. Well, so now here, as we know that a square is, say, a itself is very small. So, this a square term we can put equivalent to 0, or say it is negligible. So, if it is negligible, now what we can write, that c is equal c square, no, it is c, because we have written already in terms of root over. So, c is equal to, say, our target is to get this term gy. So, we are writing gy, means from here we are bringing a y common, here in fact we had a term a y plus a square, right. So, y we are bringing common, and 2 we are taking to that side. So, what we can write, root over gy, then here we can write, so as 1 y has come, so it will become twice y, 2 is going inside, and then plus 4 a, 2 is going and this is coming. So, it will be twice y plus a. Well, now this we can further simplify in a way that this is equal to root over gy, and let me write it in this form, that twice y plus a, fine. Here also let me write twice y plus a. Then in fact we need to write plus thrice a. We need to write plus thrice a. Well, so this twice y plus a, twice y plus a, that we can have 1, and this will become thrice a by this expression. And so let us write c is equal to root over g y, then we can write root over 1 plus thrice a by twice y plus a. Now this expression thrice a, so a is very small, and here in the denominator we have twice y. So it is quite a large expression, and as y is very large than as compared to a, so this expression will become a very small term divided by a very large term. So this we can now neglect. So if we neglect this term, say as a is very very small, as a is very very small as compared to y, therefore 3a by twice y plus a is say negligible, and now just neglecting this part, it will become c is equal to root over g y. Well, so that is the expression that we can derive, what we got in our last class. Again, starting from the first principle, we could see that for a small amplitude wave we can have the expression for c as root over g y, and if it is a suppose non rectangular channel, then what we do, that y will not represent these things properly. So what we write, that c is equal to root over g d. What d is the hydraulic depth, d is the hydraulic depth. So using this hydraulic depth, in fact for rectangular channel this will become y, but for trapezoidal channel it will be a by t. So using this expression also we can get the value of c. Well, so after that let us see that well, for a wave of this type, for a wave of this solitary wave of this kind, we can have an expression for c. But if we have a surge, and how to analyze this surge, whether the c value will be same as or the same expression whether we can use or not. Well, that first we should know what is surge. This is also in unsteady flow. This is important, important topic, that is surge. We need to do lot of analysis in fact on charges, and but here we will be just doing some limited exercise on surge, that you can see that surge is a moving wave front that brings about an abrupt change in the flow depth of the channel. So basically what we mean by surge is that, say this is the bed and normal flow is suppose moving here, and somehow a wave is coming like that. It is a moving wave front, that is why we call this as a wave front, this wave front, and say then it is moving. So this water is moving like that otherwise also, and then we have a moving wave front. This wave front is moving with a velocity say v w. This wave front is moving with a velocity v w, and this can be this we refer as a surge. In fact it can be in the other way also. Say your water level is here, and water itself is moving in this direction suppose, and somehow due to closure of gate, you have suddenly closed the gate, so water level here is rising, and then the wave can be moving in the opposite direction also. This is say wave moving upstream, and this is a wave moving downstream. So whatever may be the situation, we call such moving wave front which is moving and creating a abrupt change in the depth. See, depth earlier was like this, and there is an abrupt change. If the depth changes gradually like this, then we will not call this as a charge, but here depth is changing abruptly, and that's why we call this as a charge and a surge. And so this surge also we can express in the form of say equivalent steady state for its analysis. Well, let us see how we can represent this in the form of a equivalent flow. Well, let us consider this one, any one we can consider, but let us consider this one. Suppose this is say 1 and this is section 2. So, say 1 and 2. Why we are considering? Because this is both in the same direction, here it is in the opposite direction. That will give us an opportunity to handle a case where the flow and waves are moving in the opposite direction. Till now we have not discussed that sort of situation. So, suppose the velocity here is v1 and velocity here will be changing. Velocity here means in the entire section say v2. Well, now vw is the velocity which is moving in the opposite direction. This is a unsteady situation. At the next moment of time, this wave will be moving further, this wave will be moving further and say will not find it here. So, let us see how we can do this to keep in a steady position. Well, what we can do in this, we can apply an additional velocity in the opposite direction to the speed of the wave. Well, so please just see, we are meaning that opposite direction to the speed of the wave, but this speed of the wave is not the celerity. Celerity will be the relative speed. So, we need to apply a velocity in the opposite direction to the speed of the wave, otherwise it is moving with a velocity v1. Now, if we apply another velocity say vw, if we apply another velocity say vw in this part, then total velocity at this point will become vw plus v1, and here also it will become v2 plus vw, and then velocity of this in this direction will become 0, because it is moving in this direction, it is, and then that is why this things is not in a position to move further, it will be remaining in the same position. Well, so let us represent this and let us see how we can derive. Okay, I am now having this portion, and this equivalent steady state position we can keep here, we can draw here. So, it will be like this. Now, we have here the velocity will be v1 plus vw, and here the velocity will be v2 plus vw, and of course, there will not be any velocity of the wave, it is not moving rather. So, this is basically we can say equivalent steady situation. Well, now again for this surge, just like we were writing earlier, we can write continuity equation and momentum equation. So, continuity equation we can write here, say continuity equation, and let us put some depth value here. So, depth here is y1 and depth here is say y2, okay, y2. Well, now what is continuity equation? So, again considering unit width of the channel, considering unit width, we should mention this one, considering unit width. Okay, this will become say y1 into v1 plus vw is equal to y2 into v2 plus, sorry, it is not v3, it is vw, v2 plus vw. Well, so that is our continuity equation, and this continuity equation can give us, or from this continuity equation we can express y1 in terms of y2, and we can do those things. And then what is this v1 plus vw? That is also interesting. In fact, if from this point when wave speed or absolute speed of the wave is say it is moving with a speed vw, and then the fluid is moving in the opposite direction v1, then what is its relative speed? Its relative speed will be v1 plus vw, because both are moving in the opposite direction. So it will be, it is in fact, it will appear that it is moving faster when v1 is in this direction, vw in this opposite direction. So wave speed, relative wave speed will be v1 plus vw, and this relative wave speed in fact we call as c. So this v1 plus vw is nothing but c. Well, that we can write that equation. So continuity equation we have seen, and then let me write the continuity equation again, and let me keep the diagram here quickly. Say it is v1 plus vw, sorry, v2 plus vw, and this is v1 plus vw that we have, and depth here is y1, this is y2. Okay. Now the continuity equation we have already described. So y1 plus y1 into v1 plus vw is equal to y2 into v2 plus vw. Now we need to write the momentum equation. We need to write the momentum equation. So for momentum equation, for writing the momentum equation, we need to see what are the forces acting. So the pressure force from this direction and the pressure force from that direction, and then the momentum, change in momentum between this point and that point. So pressure diagram we can draw like that, and as we know, we have discussed that part a lot. So pressure here we can write as half of rho g into y1 square, okay, because pressure here is nothing but rho g into y1 or wy1. We can write in it as w, or we can write rho g. So writing in any form we can get it, say rho g y1, and then area of this triangle will be half of rho g y1 plus multiplied by the way y, so it will become half of rho g y1 square. So momentum equation, what we can write, the force from this side, that we can write, okay, this is continuity equation, and now we are writing momentum equation. So momentum equation we can write here say half of rho g y1 square, that is the pressure force from this side, and minus half of rho g y2 square, that is the pressure force from that side. That is equal to change in momentum, rather rate of change in momentum. So what we can write, that mass flowing per unit time and change in velocity. So mass flowing per unit time, how we can write, that discharge flowing per unit time. Well, discharge, as it is not changing from here to here, because no other flow is being added, nor the flow has been taken out. So we can write it in terms of discharge of this part, because this is known to us. What is depth y2? That is of course not known to us, because after coming of the wave this is happening, but this y1 will be generally known to us. So let us write the discharge in terms of this one, that we can write discharge in fact is equal to y1 into v1 plus vw is the, say, velocity, and area is actually y1 into width, but width is 1. So this is what the volume flowing we can say, and then this volume flowing, if we multiply it by rho, then it become the mass flowing, okay. So this is what the mass flowing, and then v square, or say sorry, not v square, this is the mass flowing and the change in velocity. So change in velocity is equal to, in fact it is v2 plus vw minus v1 plus vw. So ultimately the resulting will be v2 minus v1. So that is what the change in flow velocity. This is our momentum equation. Well, from this momentum equation we can further derive some of the relation which is required for finding the expression for C in case of surge. And well, before that, let us write the expression for C here. This is another equation, that is C is equal to, we have we can write that C is equal to, say, V1 plus Vw. That we have already explained how it is. So this is equal to C, celerity C, that is the expression for celerity C. And this expression celerity c, we can further say starting from the momentum equation we can derive it in a different form, and let us see how we can do that. Well, now we need to mention one point here, that we got one expression for c is equal to root over gy, and this equation is called Lagrange's equation of celerity. This equation c is equal to root over gy, this equation is called Lagrange's equation of celerity. Well, and now let us see what will be the expression for c in case of surge in terms of y1 and y2. Well, in general we can have it as v1 plus vw, but we do not know what is vw, and so we need to have it in a different form like that earlier we got in terms of depth y. So let us see what we can do. Starting from this, again starting from this momentum equation, we can write that this is equal to say rho we can cancel in each part, then let me take common here, say half of g, then y1 square, say half of g y1 square, if I keep here, then it become 1 minus y1 square by y2 square. Well, and on this side we can take, say y1 is here, and then v2 minus v1 is there. So what is that? v2 is the velocity. So velocity, and this expression actually y1 plus v1 plus vw, this expression is nothing but this is showing how much is the discharge. I am writing this as q. This is q means unit discharge, because we are talking about discharge through unit width. So this is equal to q. And what is our v2 or v1? v2 is nothing but q by say y1, because v2 into y1 is equal to y2 is equal to q, and v1 is equal to q by y1, because that we know. That is, again from continuity equation we know that v1 y1 is equal to v2 y1, that is also known to us. So in fact this v2 can be written as q by y2, means q is equal to v1 plus vw, q is equal to y1 v1 plus vw divided by y2. So that can be written. So well, so if we bring this q common here, let me write it in this form here, say y1 plus v1 plus vw, and then this q we can, okay, let us keep rho still here, because here also rho, okay, discharge will be coming. So this discharge is nothing but, say we can again write this part as y1 into v1 plus vw, that is what the discharge we are writing here, bringing common, and then inside this will be say 1 by, that means q we are bringing out, this q is nothing but this expression, and then here it will be 1 by y2 minus 1 by y1. Okay. Well, and as we can see very clearly that this term and this term is same, so we can just, because we are writing for discharge only, so this will be square. So this can be written as half of g y1 square and 1 minus y1 square by y2 square is equal to this. Now we can write y1 square, and then we can write here as say v1 plus vw square, then within bracket we are putting say 1 by y2 minus 1 by y1. Now let us see how we can further simplify this expression. Here, that is the v1 plus vw is nothing but c. So from that we can put the value here as c square. So y1 square and this y1 square we can cancel, and then we can just rewrite this expression in a simple form like that. C square, we have already replaced this part, that means this we are writing as c, this one, this is nothing but c. So putting that, what we can write, c square is equal to say half of g then we can write say y square y1 square minus y2 square, that we can write y1 plus y2 into y1 minus y2, and this is divided by y1 square. And then this the denominator part we can write say y1 minus y2 divided by y1 y2. That means this part, this is become y1 y2, then y1 minus y2, so this is coming here, and this is becoming y square y2 squared, and this y1 y2 square minus y1 square, that we are writing as this I mean this one say y1 y2 and y1 plus y2. Okay. Now from here what we can do, this is equal to half of g, then we can write y2 by y1. So this y1 and this y1 is getting cancelled, and we can write this as y2 by y1. y2 by y1, y2 by y1 into say it will be y1 plus y2, that will be the expression. And we can of course further simplify from this part. You can see that our target is always to get it the expression in terms of root over gy, and then whether we can have it in further simplified form. So c square, this is equal to we can bring one y from here, one y1 from here, so it is equal to say g y1, one y1 we are bringing from here, and then the other part we are writing in a different way, say half we are writing here, and this y2 by y1 is there, y2 by y1, and then as one y1 we have brought here, this will be 1 plus y2 by y1. Well, so that is the expression we are getting, and as you can see that oh, this will be y1. Okay. So c square is equal to this part. Then if we just try to take c, then we will be getting c is equal to root over g y1, then root over say half of y2 by y1, and 1 plus y2 by y1. Well, now in this expression, normally if we refer to our earlier diagram, this say y2 will not be known to us because it is coming, this wave is coming, and the y1 will be known to us, of course. So to get the value of c, then say generally we are getting the expression in terms of y2 by y1, and here it is g y1, and this y2 we need to know in many cases. So this is y2, oh sorry, this should have been y2 square by y1 square. Yes, we are taking common y1 square here, and as such it will be y2 square by y1 square, and this is y2 square by y1 square, right? And that is why we are getting this expression in this form, like that one, this one, and so this is coming in this form. Well, fine. So that way c is equal to root over g y1, and this expression we are getting in terms of y2 by y1, and this is the expression normally we use for computing surge. Okay, surge means celerity in surge, and then this help us in solving various numerical problems, small numerical problems we can solve by using this particular expression. Well, এক মিনিট এটু আকৌ কি আহিলে expression for C2 হয়ে গ'ল, continuity and momentum equation ও তাতে উলিয়াই দিলোঁ মই। আচ্ছা আচ্ছা আচ্ছা, আচ্ছা সময় কিমান গ'ল এইটো ক্লাছত? 39 গৈছে নহয়? আচ্ছা 39 মানে আৰু কিমান মিনিট আছে? 20 মিনিট। 19 মিনিট প্ৰব্লেম কৰিলেতো নহ'বগৈ, তেতিয়াহ'লে প্ৰব্লেমটো মই বাদেই দিলোঁ। 19 মিনিট আছে নহয় জানো? টেপ চলি আছে নেকি? নাই চলা নহয়? চলি আছে? বন্ধ কৰিব নোৱাৰি নেকি? অলপমান মই হৈছে? ঠিক আছে। Let us take a problem, typical problem. In fact, we will not be solving the problem as such, but we will just show how the steps need to be followed and how we can get the result. So, the problem, suppose it is like that water flows in a rectangular channel at a depth of 2 meter with a velocity of 1 meter per second. Well, say this is the channel and here water is flowing. First I am drawing by dotted line, is flowing with a depth of 2 meter. This depth is 2 meter. This is a typical problem taken from the book of Rangaraju, open channel flow. So, this is a depth is 2 meter and the velocity of flow is 1 meter per second. Well, and if discharge in the channel is suddenly triple, what will be the depth of flow? So, here it was the depth of flow. Suppose in the discharge if we suddenly triple, then what will be the depth of flow? Suppose depth of flow is increasing like that, and this will in fact continue to increase. This will continue to increase. This will continue to increase, and then wave is moving in this direction, and after some time the depth will be increasing. Now, here this is in fact our, say we can put as y2 and this is our y1. Of course, we can write either way also, and then velocity here is say v1, velocity here is v2, and then wave velocity let us put as vw. Then how we can write the continuity equation and momentum equation for this case? And what we know here is the depth y2 and this v2 is known. Velocity is 1 meter per second and depth is say 2 meters. So, that part is known and other things are not known. And what we are knowing, the discharge what was earlier flowing is just triple. So, this discharge what we will be getting here y1 v1, say considering unit width, what we will be getting y1 v1, that will be 3 times of that of the say y2 v2. Well, so how we can write the continuity equation? Again, to first make it steady, what we can do to make it steady, we can apply a velocity opposite to this vw. So, we will be applying here vw, and then if we apply vw, what will be the velocity here? Ultimately, this velocity will be changing to say v1 minus vw after applying this one, and this will be changing to, this velocity will be changing to v2 minus vw. Well, and then continuity equation we can write say v1 minus vw into y1 is equal to v2 minus vw into y2. So, that is what we can write the continuity equation. Now, here we can put the value of v2 and y2. So, what we can write, that this is nothing but say v2 is equal to 2. So, v2 is equal to 1 minus vw into 2. So, this equation will give us some information. Then we can write the momentum equation. We can write the momentum equation say. So, momentum equation can be written as say half of, well, let me give a number to this equation. Say this equation is 1, then momentum equation is equal to half of rho g say y1 square minus y2 square is equal to rho v2 minus vw. Here this is the velocity, then we are getting y2, and I mean this part is actually the discharge, and then it is v2 minus v1. That is what we are getting. And then this expression also we can simplify. Simplify means we can put the value like half of say rho g y1 square minus y2 square means 4, this is equal to rho, we can write this as rho, then V2 minus VW, that we can again write as, say, V2 was our 1 minus VW, and this y2 is already known to us, so this is 2, so this 2 depth is, we got the depth as 2 meters, so that we can put here, say 2, and then this V2 minus V1, again this we can write as 1 minus V1. Now this is, say, equation 2. Well, that what information we have a relationship between what information we have, that you can refer to the slide. We have one information like that V1 Y1, which is the discharge, which was the discharge after the charge is coming, that is V1 Y1. This is the actual discharge what is coming here, and this discharge is triple or 3 times of that V2 Y2. So we can write it like that, V1 Y1 is equal to, say, 3 times of V2 Y2, and this value we can have, that is equal to 3 into, say, 1 is the velocity into the depth 2, so this is equal to 6. So that way we can have, I am just writing the numerical value, not writing the unit here. So this is one expression, and then we have this expression, and solving these expressions we can get ultimately the value of y1, because our target is to know the value of y1, and so if we know this value of y1, our problem is solved. And to get the value of v1, we have these equations. Say this is one equation, and then here of course we have this unknown vw, and this is one equation where we have this unknown vw. So vw and y1 are the unknown that we can solve by trial and error method, and we can get, say, y1 is equal to 2.45 meter. This is just a solved problem already in the book of Rangaraju, and just I am taking here just to show how this surge problem can be solved. Well, then we will be taking up the next topic, rather the equation of unsteady flow. Well, so equation of unsteady flow, that we know that already we have discussed some of the equations of unsteady flow when we were discussing our earlier discussion on, say, a governing equation of open channel flow. For unsteady state, we were discussing about the continuity equation. The continuity equation, that as we know, it is, say, del A del T plus del Q del X is equal to 0, that we could get, and this of course we can write as, say, del A del T plus this Q, if it is Q is written as A into V, this can be written as, say, A del V del X plus V del A del X is equal to 0. Well, so here I am not taking up again this continuity equation, that you can refer, or rather we will be knowing by referring to our earlier classes. And then the two governing equations are required basically for solving the problem of unsteady flow. And then one of the most popular equation, of course continuity equation is there, then another equation that we take is the equation of motion, and this can be, of course, we use momentum principle or energy principle to get this equation of motion, and for some case we use, say, continuity and momentum equation in couple for solving the problem. Sometimes we use continuity and energy equation for solving the problem, depending on the situation where suppose energy loss is there we go for momentum couple, continuity momentum couple. So that way these considerations are there. Of course, in this class we are not going for all those detail, but we will be just discussing the equation of motion that was given, that was first deduced by Barre de Saint-Venant, and popularly known this equation as Saint-Venant equation, and that is, say, 1879, long back this equation was derived. Well, and this is a dynamic equation of unsteady flow in open channel, and for what condition? It is the shallow water wave equation, shallow water wave equation. That means why we are giving this a shallow water wave equation, because when this equation was derived, this vertical acceleration was considered to be negligible. So, vertical acceleration is negligible, and then we should know that for what condition we can apply this. And derivation of this equation, not this equation, this is continuity equation, derivation of the equation of motion can be done by two approaches. One is energy approach and another is that we can start from Newton's equation of motion. So, by both this approach we can have the derivation, and here we will be discussing how by energy approach we can derive the equation in a simple way. Okay. And then let us see what is the energy equation. Say if this is the flow and this is going like that. Well, let me take some space because we will have to write here. Say this is section 1 and section 2. So, section 1 and 2. Well, in this section 1 and 2, let us take a small length. Let us take a small length and let us write this as, say, as this small, let us write this as, say, del x, this length is. And that term is here, that term is here. So, this depth is, say, Z1 and this depth is, say, Z2. That is the elevation head up to the bed. And then up to this depth, this is y1. We are considering slope to be small, that is why we are not writing y1 cos theta or those terms, we are writing straight way, it is y1. And then here this energy is v square by twice g, v1 square by twice g, energy head up to that point. And then here in the second section, section 2, this is the y2 and the v square by twice g is supposed that much, v square by twice g, v2 square by twice g. Okay. And then we can draw the energy gradient line as this one, energy gradient line as this one, and there is definitely some energy loss. This we refer as, so when we draw it parallel to the datum, then we will be finding that there is a head loss, and this head loss we can write as HL. And in fact, this head loss is having two components. One is that it's friction loss, that is known to us because we did discuss about this friction loss during our discussion of gradually varied flow itself. And but here there will be another component, because in case of unsteady flow that local acceleration exists, just to recall briefly. Say when we say v, then it is a velocity which is a function of x and t. Of course, in steady flow it becomes a function of it is not a function of t, but in unsteady flow this become a function of t. Now when we talk about, so this change in v, say dv, that we can write as del v del t into dt plus del v del t into, sorry, del v del x into dx, del v del x into dx. Now if we write that it is a function of x and t, so if we just write it as dv dt, then we are getting del v del t plus, say, this dx dt, so dx dt divide into del v del x, and this dx dt is nothing but v. So now perhaps you can recall that we did discuss earlier also dx dt is equal to v del x, and then this is called local acceleration, this is called convective acceleration. Now in case of, say, steady flow, this term is not existing, so that problem become little simpler, but here we have this term. So this local acceleration exists, So because a acceleration is there in any, whether it is fluid or any solid body, if acceleration is there, that is a mass moving, and that mass is having some acceleration, means some force is being utilized to have that acceleration, otherwise that acceleration will not be there. So some force is being utilized to have this acceleration, and when some force is being utilized and things are moving, then there must be some work done. Force is applied and it is moving, so some distance has been moved, so some work done will be there, and some work done is there means some energy loss is there. So we can say that in this sort of flow there is two type of loss, one is HF, another is HA. So these two loss will be there. This HA is say loss due to acceleration. Well, now if we write the energy equation, so writing energy equation between say 1 and 2, between 1 and 2, what we can have between 1 and 2, this we can write says Z1 plus Y1 plus V1 square by twice Z is equal to Z2 plus Y2 plus V2 square by twice Z plus HL. Well, plus HL, or say we can say loss HL. Okay. Now this loss, as I have explained, that let me write here, say loss HL is equal to say friction loss that we write as HF and plus the acceleration loss that is say HA. So our expression become, now of course in this loss term we need to put these two. So this is equivalent to SF plus HL, already we have written here. Now we need to have an expression for these two. So HL is equal to, we know that it is HF plus HA. Now how we can get the SF? Because friction slope, we know that SF. If friction slope is SF, if friction slope is say SF, then we know that HF, that is friction loss divided by delta x is equal to SF, or we can say that SF, the slope into distance, SF into this delta x will give us the HF. So friction slope may be this like that, and we can have SF up to certain point, HF, and then this slope is actually SF, and then other part of loss is due to say this acceleration. So that is clear to us, that we have discussed earlier also. So in place of SF by delta x, or sorry, in place of SF we can write that SF is equal to SF into delta x. Well, now that, so for our next acceleration loss is there, how we can calculate that. So acceleration del v del t, local acceleration del v del t exists here. So if this is the acceleration, then the mass, suppose if we consider that unit weight of fluid, then mass is equal to say weight by, actually weight by the g. So this is here as our weight is equal to 1, so this is equal to 1 by g, and force utilized to produce this acceleration, to produce this acceleration, that is equal to mass into acceleration, so that we can write as 1 by z into del v del t. So this is what force required, force utilized. Then this forces work for how much distance? This force is working and then acceleration is being there, and then the fluid is moving, this mass is moving from here to here. So the distance of say delta x, it is being moving. So what is the work done? And distance moved by this unit mass, by this unit weight, rather by this unit weight of fluid, is equal to delta x. That is what we are considering. Therefore, the work done, how much work is being done? Work done is equal to 1 by g del v del t into del x, del v del t into del x. Well, so this is the work done, and what this work done is, that is the energy loss, energy loss. So energy loss is equal to, that means 1 by g del v del t into delta x. So finally, how we can write the head loss? So this energy loss is nothing but h a. So this energy loss due to acceleration, that is the work done due to produce that acceleration, and that is the energy loss, we can write like that. Therefore, so what we can write, that head loss HL is equal to HF, what we can write, HF plus HA, okay, HF plus HA, and that HF we can write SF into delta x, and then this HA we can write, that is the acceleration loss, 1 by z, then del v del t into delta x. So putting this value of HL in our equation of energy, this one, then we can get a simplified expression, and then manipulating with that expression, finally we will be able to derive a equation of motion, and that we will be doing in our next class. And then from that we will be also trying to see how this equation can be solved, and then by solving this equation, how we can get solution to our real life problem of open channel flow. So thank you very much.